So let us understand what is mean by an oscillation or oscillatory motion. Okay, so let me give you the definition, then I will explain. Okay, so to and fro motion. Okay, to and fro. Yeah, actually, I just need to and fro periodic motion, to and fro periodic or harmonic motion. Okay, about its mean position. See, all are keywords here. Whatever I given here, all are keywords. Okay, to and fro, periodic, about its mean position. I will explain everything in detail. You don't have to worry. See, to and fro motion means it's very simple. Okay, so like going and coming back, going and coming back. That is what periodic motion we already know. Now listen, I will take an example so that you will understand it better. Let us take an example of simple pendulum. Okay, simple pendulum. Right, so what is a simple pendulum? See, simple pendulum, one end we will be having a hinge and we will be having a thin thread and there will be a point mass, okay, a ball which is attached to it. Okay, this is a bob, okay, with a mass m. This is basically a point mass. See, there are different pendulums. There are compound pendulums also. So what is the difference which this simple pendulum carries? Let us take the length of this thread. Okay, there is length of the pendulum to be L, and the radius of this small bob, there is small mass, that ball is there, right? That radius was R. So when can I call it to be simple pendulum? When it is the simplest form of the pendulum. See, as I said, there are compound pendulums. When I am able to make the pendulum very simple, simplest form, then I can call it as a simple pendulum. The first condition was mass of this thread. Okay, the thread which is connecting the bob is there, right? That thread mass is highly negligible. Very, very, very thin thread. Okay, so that is one of the simplification. Second one is this mass is to be treated as a point mass. This mass is to be treated as a point mass. What does it mean by a point mass? Listen, when this length, okay, when this length from the hinge, okay, this is the hinge point. From hinge point, if length of this thread, that is length of the pendulum itself, if this is much higher, okay, length of the pendulum or length of the thread, if it is much higher than that of R. Okay, so compared to this L, if R is very small, I can simply take this mass to be a point mass. Instead of considering it to be a continuous, a distributed way, I can simply consider it as a point mass. That's it. Okay, so I can, for treating this mass as a point mass, length of this thread has to be much higher than that of radius of the bob. These are the two conditions, okay, to make a pendulum simple. Okay, to make it as a simple pendulum, right? This simple pendulum exhibits oscillatory motion or oscillation. What does it mean? Listen there. What I did there was I holded this bob and I just given some initial displacement. Okay, I just holded it and I kept here and I left. Okay, so as you could see here, I holded the bob, I kept to this place, I lifted it to the extreme position. Okay, I lifted it to the extreme position and then I left. What's happening? It's coming back. It is reaching its mean position. This is my mean position. Okay, when nothing is done, this is my mean position. So from extreme position, if I lift it to extreme position, let us take for an angle theta. If I lift it to the extreme position and if I leave it, obviously it's going to come back. Why it is coming back? I will say obviously it's going to come back and it will reach. It won't reach there. It will reach the mean position, and continuously it will move and then it will reach the another extreme position. And this is going to happen. Okay, after that what happens? It goes here, reaches mean and here and again come back mean, and this happens and finally it will come to stop. So from one extreme to another extreme, from one, it's a to and fro motion. Okay, from here to here, to and fro motion through mean position. Okay, about mean position. Okay, so that is what very important. So this about its mean position is important. I will say why. Consider sine. Okay, sine graph. What is the sine graph? How I will get? See, this is my sine graph. Is it periodic? Is sine graph periodic? Of course, yes, it is periodic because it's getting repeated. It's getting repeated after some time period. It's periodic. Fine. Is it oscillatory? Is it oscillatory motion? Of course, it is oscillatory. Why? Because you could see that it is repeating about its mean position. This is my mean position, right? So about its mean position, it was repeating. So that is why it is oscillatory. Fine. But what about mod of sine? Mod of sine x means what? Completely in positive axis. This negative term will come to positive side. So the negative term will come to positive side, which means I will get a graph something like this. Now my question, this is oscillatory. Okay, my question, is it periodic? Of course. See, this is periodic and oscillatory. Anyways, if a motion has to be oscillatory, it has to be periodic. Okay, is it periodic? Yes, it is periodic. Why? It's getting repeated, right? This is my time period. After this, I'm getting the same. So it's getting repeated. It's periodic. But can I say it is oscillatory? Of course not. It's not oscillating. It's not undergoing to and fro motion about mean position. So it is not oscillatory. It is not oscillatory. So for a motion to be oscillatory motion, for an oscillation to exist, the periodic motion, the to and fro periodic motion should happen about its mean position. And one of the example here was the simple pendulum. This is periodic, obviously. Okay, it's getting repeated after some time period and it is happening about its mean position. Okay, right. There are few points to be discussed here. The first point is regarding the different values, okay, displacement and velocity and acceleration. First of all, as I am lifting it here and as I am keeping it here at this position, okay, at this position, I have maximum displacement. Okay, comebacks here, zero displacement. There is no displacement here at all. Again, lifting back here, maximum displacement. Okay, of course in another direction, but it's a maximum displacement, right? This is the maximum distance it can travel. But what about velocity? What about velocity here, extreme position? See, when it was moving, this will reach here, it will pass for some time, right? It is an extreme position. We have dealt with extreme position in many cases in that slider crank mechanism and all those things. When it reaches extreme position, it will pass and again it will come back. So when it was under extreme position, my velocity will be 0. And when it reaches mean, it will be maximum. And again when we reach here, another extreme position, it is 0. Now what about acceleration? Obviously, V was max, so acceleration will be 0 here. But what about extreme positions? What will happen in extreme positions? See, listen, I will explain to you. I can directly give you the answer, but let me explain with some, what I could say, some free body diagram or something. Okay, just listen. This is my initial position, right? And now it has reached this position, let us consider. Okay, let us consider it has reached the extreme position. Okay. This angle is theta. So what are all the forces we are going to, if I want to draw the free body diagram, the first force was gravitational force. This is m into g. Mass of the bob is m, acceleration due to gravity g. Okay, and there will be tension right here in the string. There will be tension. So let the tension be T. Okay, let the tension be T. Now I can resolve this mass into two directions. One is along this thread. Okay, one is along this thread. Another one is perpendicular to it. So first of all, what is going to be this angle? See, from geometry I can say angle between this and vertical line is theta. Okay, and this is my mg, and this blue color line was what? The same line, right? Blue color line was same line. So if this is theta, then this will also be theta, basically from geometry. So if this is mg, I can say this is mg cos theta, and perpendicular to it, this is going to be mg sin theta. Now, because of this mg cos theta and t, of course there is going to be, because this bob is undergoing circular motion, it's obviously circular motion. You could see this is a circular path. This is a circular path, so this bob is undergoing circular motion. Fine. So there is going to be acceleration radially also, centripetal acceleration. But I am not very much interested in that radial acceleration because I am focusing on this motion. I am focusing on this motion only. So now you might get a point here. See, I said that I lifted this and I kept it here, and if I remove my hand, it will oscillate, right? It will come back to this mean position and it will reach the another extreme position. Why it is happening? Because of this force, and this force is called as restoring force. Okay, this force is called as restoring force, and that is why I am more concerned about this motion. I am not concerned about the forces which is acting here, acceleration which is acting here. I am concerned about tangential acceleration which is tangential to this curve. Okay, so this force mg is acting perpendicular. It's acting perpendicular. Perpendicular to this thread t, which indirectly means this is tangential to the circle. Okay, if I trace a circle here, approximately tracing, if I trace a circle here, this mg sin theta is tangential to it. So what type of motion it is? It's a dynamic equilibrium, right? It was under dynamic equilibrium. Obviously it is under dynamic equilibrium, and if I focus only on tangential, summation of tangential force will be equal to mass into acceleration. Acceleration of center of gravity, tangential acceleration, don't forget it. Again, why I am taking acceleration of center of gravity? Because it is a point mass, so I can simply treat it as a single point. So if I treat it as a single point, I need to take center of gravity as my reference. Okay, all these things we discussed in engineering mechanics. Okay, summation of ft. So what are all the tangential forces? We have only one force, mg into sin theta, mg sin theta, which is equal to m acceleration acgt. Okay, m I can cancel. So finally I will get tangential acceleration as g sin theta. Now see, g is constant, right? G is constant. If theta increases, obviously this theta cannot cross 90 degree. This theta cannot cross 90 degree, and we know that from sine curve. Okay, from sine curve, when it was from 0 to 90 degree, if I increase my theta, my sine value is going to increase. It will increase, my sine value will increase from 0 to 1. So if theta increases from 0 to 90, my sine increases from 0 to 1. What if my theta reaches theta max, maximum possible? When theta will be theta max? When we are in extreme position. My theta will be theta max. So when I have maximum theta, my sine value will also be maximum. I will be having maximum sine theta. So my acceleration will also be maximum. Let me repeat one time. Theta value has to lie between 0 and 90. Obviously, it is an acute angle. So when theta increases from 0 to 90, sine increases from 0 to 1. So when theta reaches maximum value, when theta will reach maximum value? When the bob was in extreme position. So when the bob was in extreme position, theta will be maximum. When theta was maximum, sine theta will be maximum. So AT will be A maximum. Okay. So when theta was at the extreme position, theta will be maximum, A will be maximum. Wherever other position you take, according to the theta, you substitute the theta, you will get the acceleration. Okay. So what happens? Theta will be 0 in the mean position. Here it will be like there will be an increase, and here it is going to be maximum, and here again it's going to be maximum theta. Okay, so I hope it is clear, the basic idea about this oscillatory motion and all those things.